So we're going to look at vapor pressure some more, and we're going to look at using vapor pressure curves to talk about things like intermolecular forces, boiling points, and whatnot. You can use a vapor pressure curve to do those things, and how we get that is we use the manometers to measure vapor pressures at various temperatures. So in order to talk about all of those things, we should probably talk about a few things and review a couple concepts. The first thing that we want to talk about again is normal boiling point, this idea of a normal boiling point. Most substances can have a normal boiling point. That means that they will boil at a specific temperature, but at standard pressure, so at sea level. And remember that standard pressure is 101.3 kilopascals, or 760 millimeters of mercury, or 1 atm. Basically, just different units for the same thing. So that's what makes it normal. Now remember, water normally boils at 100, but it can boil at different temperatures based on the pressure around it. We've also learned that boiling is the point at which vapor pressure is equal to or greater than the atmospheric pressure. So at minimum, it has to be equal to the pressure of the atmosphere. And that's why boiling is so hugely impacted by the pressure of the surrounding air. If you lower the pressure of the atmosphere, so like, under standard pressure, you need 1 atmosphere. If that's standard pressure, then the pressure of the vapor has to at least be 1 atmosphere. But as you go up, let's say like up a mountain or something, and let's say this becomes 0.8 atmospheres as you get higher in altitude, now the vapor pressure only has to get to 0.8, so it won't take as much energy. So really, boiling is mainly affected by the pressure of the atmosphere. Now, another word that you may have heard before that we should probably clarify a little bit is this word volatility. Lots of people think of volatile things as things that are explosive. Like you hear somebody say, oh, it's a volatile situation. It's an explosive situation. Volatility is really just liquids or substances, in terms of chemistry anyways, that evaporate really quickly and easily. They have very low intermolecular forces. Think of the things that we know evaporate fast. Alcohols, gasoline. A lot of those things are flammable and could be explosive, but really, in terms of volatility, it's just how quickly they evaporate. They have very high vapor pressures. So I use alcohol as an example. So just a word that we hear sometimes in the real world that kind of means a little bit something a little bit different in chemistry. The meaning has changed a little bit when we get out in the real world. So now we're going to look at vapor pressure graphs. So using a manometer, we can measure the vapor pressure of a liquid or above a liquid at different temperatures. And we can use that graph to find normal boiling points, find your boiling points at different pressures, compare the intermolecular forces, how fast things evaporate, these kinds of things. So I've got some examples we'll go through, and I do understand this graph is not the greatest. I do not like this scale, but we're just going to deal with it as best as we can. I'll try to give better graphs on the lessons and assignments, or on the worksheet assignments and tests and things that you'll have to use. But this will at least show you or give you the gist of what we're trying to do. So if we're looking at this graph, you can see that there's 3 different substances, CH30, CCl4, and H2O. And what we've done is we've measured their vapor pressure at different temperatures, starting at 0 and working our way up to over 100 degrees. So in this first question, it's asking, what's the vapor pressure of trichloromethane, which is CHCl3, at 0 degrees Celsius? So our 0 degrees Celsius mark is right here. So I'm looking at CHCl3, so that's about right here. And again, the scale is not the greatest. So I'm going to kind of put a line about halfway between 0 and 200. So I'm going to say that's just a little bit over a quarter of the way to 200. So I'm going to say it's around 60-ish degrees Celsius. So I'm going to say, 60 millimeters of mercury, mmHg. Now, again, because of this scale, I'm just going to say it's about equal to that. So you guys know that this is equals, this is not equals. This means about equal to. So we're going to say that for now. And most of our answers will be like that with this graph. So all I'm doing is just looking at the temperature to find the pressure. Now, we can also do the very opposite of that. So we can just, now, given a pressure, we can figure out what the temperature would be if it had that pressure. So we're looking at carbon tetrachloride, which is CCl4. So I'm going to go at 600. I'm going to draw a line across to CCl4, which is here. And I'm going to drop a line down as straight as I can. And looking at that, it's falling somewhere almost bang in between 60 and 80. So I'm going to say it's about 70 degrees. So if we heat CCl4 up to 70, it gets a pressure of 600 millimeters of mercury. Now, in this question, it says, which substance has the highest vapor pressure? And lots of times students will look at this and they'll say, oh, this one, because it goes the farthest. But vapor pressure is this axis. So we're looking for whatever is the highest. And yes, I can see that this keeps going up, but so do these. So at any time or at any temperature, we should be looking upwards to see which one would be the highest. So if I start here, oh, CHCl3 is the highest. Here, CHCl3. Here, CHCl3. Here, CHCl3. As we keep going, remember, this keeps going way off the chart. So it's way off of there. So no matter what temperature we're at, CHCl3 will always have the highest vapor pressure because it just keeps rising. It doesn't stop at this pressure here, at this temperature. You can heat it up hotter. So that would be its vapor pressure. So if we want to talk about which substance would evaporate the fastest then, well, the one that has the highest vapor pressure means it's making the most vapor. So that would have to be CHCl3. It would evaporate the most quickly because it makes the most vapor. Slowest would, in this case, have to be water because it has the lowest vapor pressure. At any temperature, water is always below the other ones. So water is our slowest. It has the strongest forces. So that's where we're at here. So water would have our strongest forces, and weakest would be CHCl3. Now, the next question is, what are the normal boiling points? So again, remember, normal boiling point happens at 1 atmosphere or 760 mmHgs, which is 101.3 kilopascals. So this graph is measuring in millimeters of mercury, so we're looking for 760, and they were nice enough to give us a line at that pressure. So I'm going to use the line that they gave me. So each of the substances, they've actually even drawn a line down. So there would be my boiling point of CHCl3 at standard pressure. So I'm going to say that's like 61, 62 degrees. So CHCl3 is, let's say 62 degrees. And CCl4 is a little bit below 80. It's like 78, 79. I don't know, let's say 79, I guess. Maybe it's 78. CCl4. Let's go 78 because I went 62 on the other one. And then water would be exactly 100 because that's the normal boiling point of water. We know that one. So H2O is 100 degrees Celsius. And we can see that on the graph. So that's where we get the normal boiling point. Again, it doesn't always have to be 100 or 62 or 78. That's its normal boiling point at standard pressure. So if we go to Banff, though, Banff has a lower pressure than Winnipeg. So we're looking at CCl4, and we're going to see what temperature it's going to boil at in Banff. So I'm going to look at the scale here, and just to help myself, I'll draw a line halfway, so that would be 700, and halfway between that would be 650. So I don't know, somewhere in here. Okay, so at 635 millimeters of mercury, we're going to draw a line over as straight as I can, and then down. We're doing CCl4. I'm going to say it's just above 70-ish, so I don't know, like 70s here probably. Oops, that's a little bit off, about there. So let's on 72. So this is going to be about 72 degrees Celsius. At that temperature, the pressure of CCl4 would be equal to the pressure of the atmosphere. Because remember, for boiling to happen, PVAP has to at least be equal to or greater than the pressure of the atmosphere. So at that point, it's equal to. So now we can start to boil. And I believe those are kind of all the examples. So now you can use the vapor pressure curves in your workbook to do some of the same types of questions.